This is the introduction to chapter 15 on vector fields. So this is the last chapter, and there's going to be some new material, but the thing to keep in mind is you'll see there's a lot of stuff we already seen, and there's a lot of stuff that we will review. So it's a good cap on this whole class, okay? And to appreciate what we have done, I did this little table here, okay? So what have we studied? We have studied functions in general, right? We started with vector valued functions, that is function from R to R2 or R to R3 or R to Rn. So those essentially are curves, right, in the plane or in space. So we saw conics, we saw lines, and we saw curvy things. And the important concept there was the velocity vector, okay, when you take derivative coordinates by coordinates with respect to the parameter, and that's the vector that is tangent to the curve. All right. Then we move to function of several variables, that is functions from R2 to R, R3 to R, or Rn to R. And in this case, geometrically, we get a surface. And well, R3 to R, we cannot really present it in 3 dimension. I would need 4, but we can look at the level surfaces, etc. And the important concept here was the gradient. Okay, very, very important concept, the gradient of a function. Okay, so that was in chapter 13. 14, we did integrals of such function. And at the very beginning, we looked at planes, which is the linear functions. Okay. All right. And now we look at vector fields. So we're going to look at function from R2 to R2 or R3 to R3. And more generally, we could look at Rm to Rn. Okay. And so you see the difference. Now we have many dimension in the domain and the image. And we're going to see again important derivatives, and those are called the curl and the divergence. Okay. And the climax of this chapter and of this class, in some sense, is putting all these things together and get some generalization of the fundamental theorem of calculus, which says in 1D that when I integrate a derivative of a function from a to b, this is just f of b minus f of a, right? And it relates the integral to the derivative. So we're going to see some generalizations of that later in the chapter, when we're going to relate these derivative notions to multiple integrals that we saw in chapter 14. All right, so what is a vector field? Again, as I said, it's a function from R2 to R2. So how can we represent this? So let's do an example. So this is a vector field from R2 to R2. I have 2 input, and I get 2 output. Okay. And the output is minus y for the x coordinate and x for the y coordinate. Okay, so I take essentially the xy coordinate of the input and I swap it and I put a minus here. So how can I represent this? So either I do, if you want, the elementary way, where I have the domain and the image, and I send a point to the image, its image. So 1, 2, for example, in that plane is sent to minus 2, 1. That's one way to represent it. But another fruitful way is to actually think of the output as a vector sticking out from the input. Okay? So in other words, at the point 1, 2, the output is minus 2, 1, so I put the vector minus 2, 1 sticking out from that point. And let's say I look at the point 2, 2 as input, then the output is minus 2, 2, and I put a vector sticking out there. All right. So those are, that's why it's called vector field in a way. So at every point in R2, I get a vector, so it's a field of vectors. Very good. So those functions are not new. So those vector fields are not new because when I take the gradient of a surface, I get a vector field. So let's do an example to convince ourselves of that. So if I take this function, so this is a function now from R2 to R, I get a number, okay? X squared y plus 3xy cubed. This is a number, depending on the input xy. Now if I take the gradient of that, so the x derivative of this is that, and the y derivative is this. And therefore, for every xy, associate a vector, and that vector is the gradient. So that's a vector field. Very good. We can do that also from R3 to R3. So I can take now a function of 3 coordinates, x, y, z. Okay, so now this gives me a number. I can define a vector field by taking the gradient of that. Okay, so the gradient of that would be the x derivative to x for I, the x coordinate, 2y for the y coordinate, and 2z, 2x to y, 2z. And again, for every x, y, z, I get a vector, which is 2 times x, y, z. All right. So questions, are every vector field actually the gradient of a function? The answer is no. Those vector fields are special, and they're called conservative. So a vector field is said to be conservative whenever it's the gradient of a function. And if it is conservative, then that function for which it is a gradient is called the potential. Okay? And that's obviously a physics terminology. So when is a vector field conservative? Well, it is conservative if and only if the mixed derivatives are equal. So what does that mean? Again, let's do an example, and it will illustrate why this is true. So let's take this simple example where the vector field is 2xy for the x coordinate and x squared minus y for the y coordinate. So if this is actually the gradient of a function little f, then 2xy is the x derivative of that function, and x squared minus y is the y derivative. But we know that the mixed derivative has to be equal. So when I take the derivative with respect to y, I should get the same thing as when I take the x derivative of this guy. And this is the case here because I get 2x for the first and 2x for the other. So they're equal. Okay? And when the mixed derivatives are equal, so it's conservative, I can actually find the potential, the little function f easily. I just have to integrate. Because I know this is the x derivative of the function f, so I integrate with respect to f, okay, with respect to x. So I get x squared y, and then I also have to add some function of y, okay, because I integrate with respect to x. When I take the derivative with respect to x, this would go to 0, okay? So I can check that the partial derivative of x of this is actually the right thing. Now I can also integrate in y, the y derivative, and I get x squared y minus y squared over 2 plus a function of x, which would go to 0 when I take the y derivative. And then what you do is you put everything together. You look what you have. I have x squared y in both, so clearly that's part of my potential. Minus y squared over 2 is part of my potential. And if you want this, it is the hidden function of y that was here. And do I have a hidden function of x here? No, I don't. So I don't include it. And then I have some real constant c now. Okay? So that is my potential. Easy to verify if I'm right. I just take the x derivative, I get what I have. The y derivative, I get what I want. So this is really the gradient of that function. Always double check with the derivative. It takes no time. Okay, what about this guy? The vector field that at the point xy, I associate the vector minus yx. Is that conservative? No. Why? When I take the partial derivative with respect to x, okay, so right here, I guess, the partial, so this should be, if it were conservative, it would be the x derivative of little f. So when I take the derivative with respect to y of that, I get minus 1. And it should be equal, if the mixed derivative are equal, it should be equal to the x derivative of the other side, which is 1. And those two things are not equal. The mixed derivative are not equal. It is not conservative. All right. What about 3 dimensions? So in 3 dimensions, I have mixed derivative xy, xz, and yz. Okay, so I have to check them all. But there's a nice compact way to put all these conditions in one object, and that's looking at the curl. So it's a good time to actually define my derivative of a vector field in R3. Okay. So if I have a vector field in R3, so it's from R3 to R3, so to every point x, y, z, associate a vector, so 3 coordinates that I called f1, f2, f3, and those are function of the point. Now I have the divergence of f, called div of f in the book, or I prefer the notation gradient or nabla dot product f. I'll tell you why. So what is the divergence of f? I just take the x derivative of f1, y derivative of f2, and the z derivative of f3. I just add them up. Why is this notation good? Well, the gradient, I can think of it as just a vector del x, del y, and del z in each coordinate. Okay? And then if I apply this to a little function f, when we compute the gradient, I get the partial derivative in x, the partial derivative in y, and the partial derivative in z. Now, if I do the dot product with that vector, gives me the 3 coordinate of the vector fields. What I get is the derivative of x of f1 plus I add. This is no longer a vector. It's a dot product, so it gives me a number. Del f2y plus del f3z. So that is a divergence. It's a number, not a vector. The other operation you might imagine is related to the cross product. Same with the derivative operator, del x, del y, del z in each coordinate, and f1, f2, f3 for the coordinates of the vector field. And what you do is compute the curl of f. So the book used curl instead of that notation. So it's better, this notation, because it tells you how to compute it. It's a cross product. So you take in the I coordinate del y f3 del z f2 minus in the j this diagonal and k these diagonal. All right, and so the curl is actually a vector with 3 coordinates. And now you can see that actually f is conservative if and only if the curl is the 0 vector. Why? Because if f1 is the x derivative of function f, f2 is the y derivative, and f3 is the z derivative, then this guy being 0 is saying that the yz derivative of that function is equal to the zy derivative. And same here for the xz derivative, and same here for the xy derivative. So this condition is really putting all the mixed derivative being equal condition together. All right. Now we will see as we go examples that actually will convince you that the divergence of a vector field is a measure of how much a vector field flows out of a point. Okay? And the curl is a measure of how much a vector field whirls or rotates. So it flows out into at a point, and you look at the arrows sticking out of that point, and whirls mean you look at a point and you look how much you essentially rotate. Those arrows rotate around that point. Okay? So let's do an example to convince us of that. So if I take this vector field, x, y, z, okay, what's the divergence? So it's easy. I just add the partial derivative for each coordinate, and I get 3. Now if I compute the curl, okay, so it's a cross product between the derivative operator and x, y, z, And if you compute it, you can see that I get the 0 vector here. The 0, all those partial derivatives are 0. So I get the 0 vector. That's not too surprising. So it's a vector field in R3, but I will plot it in R2. So what happens is at the point x, y, z, associate the vector that is in the direction of x, y, z. So like this, it points out, right? If I take this other point x, y, z, I associate the vector that points towards that point. So it's that vector. So everything, if you want, is sticking out. And so the divergence tells you that if you want things are flowing out of a point, and nothing rotates here, the curl is 0. And this is to be compared with we'll do example of other when we have the curl and when it rotates. So we'll see that later. All right, so thank you for listening, and I'll see you in class.